What do your bones, a car battery, Dawn dish soap, and let's just say jewelry have in common? Well, let's stick around in this lecture and we'll find out. Today, we are going to talk about density. And if I could sum up what this lesson is going to be about in one statement, my objective statement would be that you would be able to define and calculate density of a substance. In saying that, we're going to go through whether it's real life examples, mathematical examples, and all kinds of different worked out solutions with this. So stick around, let's go through this, let's crank this density out. So first thing we want to go to is talking about osteoporosis. Okay, with density, we want to apply this to the real world. So let's talk about it in the medical setting. Okay, so osteoporosis literally means porous bones. This is a result from a lower bone density. So what is bone density? Well, there should be a video coming up on the screen now. And what we see here is as your bones, if we want to see a cross section of your bones, so we take your bones, we cut them in half, we see that there is some mesh in there. Okay, that thick mesh or thick webbing they have in there, that creates stability in your bones. It makes them strong. What happens with osteoporosis is, as we see with this video, sometimes your bones that webbing inside them can start to shrink. And that means the density or the amount of mass inside that given volume of bone, okay, is going to decrease. Well, think about it this way, like if you have less webbing on the inside of your bones, okay, they're going to have less mass in general. A healthy human bone, its density is roughly about 1.0 grams per cubic centimeter. While someone who is suffering from an extreme case of osteoporosis can have a quarter of that or less than a quarter of that, where records being shown that there's a bone density of 0.22 grams per cubic centimeter. Well, what does this do and what does this have to do with, what does this do and what does this mean? Like, what's the big deal about a lower bone density? Well, lower bone densities can lead to bones breaking more easily. Okay, so we see a healthy bone on the left has a lot of that spongy material, while if we look on the right, that bone, we see a lot of empty space in there. This can result in more brittle bones, so bones that are easier to break, and also if you see older people, they can have that hunched back. That's not just because of posture. That's also because of, let's say, these bones, when you put weight on them, okay, if they don't have this ability to be strong, then they could start bending. And so we see that there's a bend in them causing what we see is that hunchback because there's so much weight on them. Let's just continue with diagnosing it, and so we can see it in the real medical world because we're trying to apply this. This is two x-rays, one of a normal human being and then one of a human that suffers from osteoporosis. How x-rays work is you shoot these x-rays into a substance. If it hits a solid thing like a bone, then it's going to absorb. The more solid it is, the more that x-ray is absorbed. Thus, when it goes to the other side, it doesn't make an imprint of the black on the other side. Okay, so that's what this does, is make the white portion of what you see in your x-rays, the absorption of those x-rays. So if we look at the left versus the right picture here, we see that in the left picture, a healthy bone, okay, you can see those bones a lot easier. There's a lot more dense white stuff, okay? That means that x-ray was absorbed. That means it's a healthy bone. There was a lot of density in there to absorb that x-ray. While if we look on the one on the right, we see that it looks a lot darker and it almost looks opaque, or like you can see through it. And that's because it didn't absorb as much of those x-rays because there's not as much of a density there. That webbing is less prominent. So I wanted to just get you with density on this. Let's continue and talk about the difference between density and buoyancy, or let's just be honest, how they are related. Okay, general rule of thumb is The less dense a substance is, the more likely it's going to float. Okay, so for instance, your boats, okay, whether it's a warship or it's a little raft, those boats are less dense than water, thus allowing them to float on water. Okay, so we talked about bone density. Let's go ahead and bring Dawn dish soap into this. Think about oil and water. Okay, your oil. Okay, whether we have an oil rig spill or if you're just in your kitchen and you put oil on top of water, okay, your oil is less dense than your water, so it's going to rise to the top. It will float on top of your water. Well, how does this apply to Dawn dish soap? A good amount of time ago, we'll say that, there was a big oil spill. And if you ever noticed, Dawn capitalized on this great marketing opportunity. Okay, they always have a little ducky on their dish soap, and it used to be because they were the dish soap that cleaned oil spills up. You can get rid of oil with Dawn dish soap. The reality is Dawn dish soap is nothing different than any other dish soap. They just used it as a great marketing opportunity. So how does this apply to density? Well, Dawn dish soap, if you put Dawn in water, well, what do we see? Once it mixes with the water, you see the bubbles come to the top. But if you just pour that soap into water, it's going to sink to the bottom. So it's going to be more dense than your water. Let's take it one step farther. How about this? Here's your concept checked. What about ice in water? What does ice do in water? And what does that tell you about the density of ice, even though it is just frozen water? So I'll give you a second. So now we're back here. We're going to talk about what is density. Well, technical definition is density is to measure how much mass is contained within a given volume. In other words, how tightly packed are the molecules within that substance. Okay? As we talked about in the last slide, we can have a giant warship float on water, meaning its density is less than water. But we can also have something like soap sink in water, so that means its density is more than water. Well, how can soap sink in water when it seems so little compared to a giant warship? Well, because the mass per that volume is different. And so we're going to talk about that. Density is an intensive property, meaning that it is independent on the amount of substance. Okay, so what does that mean? Think about it this way. Okay, if I have a cube of copper, okay, whether it's a 1 pound cube of copper or a 250 pound cube of copper, that is still going to have the same density. The mass might change, but the overall density is going to be the same. And so that's what we mean by an intensive property. Okay, mathematically, we have 3 ways we can solve for density. We can just do the straight formula. Density equals mass over volume. If that's hard for you to remember, my wife gave a great example that she learned in high school. Think about density equals a heart. Okay, the top part of your heart is your mass, while your bottom part is your volume. So you have the little semicircles on the top, and then that V at the bottom, it makes a heart up. Okay, so density equals a heart. If that works, it works for you. Or you can think of the density triangle as shown up here. All you have to do with the density triangle, it's kind of like a hack, is cover up whatever portion you are looking for. So if I'm looking for mass, I'd cover up the mass, and it says density times volume. Well, there's my formula for finding mass. If I'm looking for the density, I would cover up my D. And what I would have is mass over volume. Well, we know that's the formula for density. If I'm looking for my volume, that would be mass over density. So that's just kind of a little hack and a little cheat code for you. With density, though, it is important to know one thing. Whichever way you choose to solve density problems, you need to make sure everything's in the appropriate units. Okay? So if it's a solid, things need to be in grams per cubic centimeter. If it's not in that, you need to convert before you even do any of your other calculations. If it's a liquid, it needs to be in grams per milliliter. And if it's a gas, it's grams per liter. So if I'm given so many milliliters of a gas, and I'm given how much the mass of it is, the grams, I still got to convert those milliliters of my gas to liters before I do my density calculation. So understand, like, this is going to be the hard part of density problems. The hard part of them is dealing with getting the correct units. That's where the most work is going to happen. So we've addressed mass, okay, that has to be in grams, and its mass density is mass per volume. Well, how do we find the volume of a substance if it's not just given to us? Because let's be honest, it's not going to always just be given to you. Well, we know from geometry and algebra there is some, for regular shapes, there is some formulas we can use. For instance, a cube or rectangular prism, we can use length times width times height. And a sphere, we can use 4/3 pi r cubed. And if we have a cylinder, we can use pi r squared times our height. But what about something that has a weird shape that's not one of those like shapes we know this specific volume formula for? Let's say, in this case, like a dinosaur. Well, what we have to do is a water displacement test. In this case, what we do is we have our water at a certain amount, so I think it's roughly, in this case, 5.8. We then drop 5.8 milliliters, we'll say, and I dropped my dinosaur in there, and it raised it up to 6.6, we'll say 6.6. Okay, so we started an initial at 5.8, we got up to 6.6 milliliters. We find our volume just by subtracting our final volume with our dinosaur in there and without our dinosaur in there. So 6.6 minus 5.8, that's roughly going to give me a 0.8 milliliter change. So that means the volume of this dinosaur is 0.8 milliliters. Okay, so you have to do a water displacement test for anything that is a odd shape. Okay, so we've talked about a couple of things from the beginning. We talked about the density of your bones. So what does your bones have in common? Density. With dish soap, okay, a higher density, may sink in water. Well, your bones can fluctuate in density. Okay, let's talk about your car battery. The density in a car battery, how a car battery works. Car batteries have a liquid in them called sulfuric acid. The density of the car battery changes as it discharges. Okay, so what happens is that concentration of sulfuric acid is going to decrease. What we see here is that sulfuric acid is going to let off ions or charged particles. Okay, and those charged particles are what's going to power the electricity of your car. So as we're releasing those charged particles, we're not kind of replacing them. So that's going to decrease the amount of sulfuric acid in your battery. Once the density reaches a certain point, it can't discharge any more sulfuric acid ions. Because it can't discharge those ions, we can't produce electricity. So what's going to happen here? Well, we're going to have to either increase the density of sulfuric acid by putting more sulfuric acid in the battery, which as a normal human being you're not allowed to do. You can't get that. Or what we do here is, if you have a dead battery, what's the common practice? You jump off the battery. Okay? You add more of an electrical current to it. In other words, you add those discharges back into it. You take the discharges from one battery and add it to a different battery. Okay? So, by doing that, you then can, for lack of a better term, you can milk more of that sulfuric acid ion concentration out of that battery now that it has been recharged back up. Or, let's be honest, sometimes we might have to get a new battery. When dealing with the density problem, what are our steps to solving this? Well, first is to convert all units to appropriate units. That's why I said it's the hardest thing to do. Second, we identify what we're looking for, whether that's the mass, the volume, or the density of a solid, liquid, or gas. Appropriate units are the important thing. And at the end, our last step is just plug everything in, whether you're using the density equation or density triangle, and get whatever variables you're missing. Okay, so let's work a practice problem. A liquid has a mass of 95.72 grams and a volume of 20.54 milliliters. What is the density of that liquid? Okay, the first thing we need to do is get our density formula. So density equals mass divided by volume. Okay, from there we understand that we're dealing with a liquid, so we need it to be in grams per milliliter. And we go look at our formula and our problem. Okay, we see we're giving a mass of 95.72 grams and a volume of 20.54 milliliters. Both of these are in appropriate units. So all we have to do is just simply plug this in. This is super easy. So what we're going to do is take 95.72 grams over 20.54 milliliters. This is going to give me a density of 4.66 grams per milliliter. And that would be my answer. Okay, let's work another one. Here's question 2. The mass of a gas whose density is 0.785 grams per liter occupies a volume of 3.1 liters. So what is the mass of this? So what we understand here is the density equals mass divided by volume. Okay, if we want to rearrange that equation so that we get mass equals density times volume. Okay, when we look at this and we see we have our density in grams per liter and we have our volume in liters. Well, with a gas, it needs to be grams per liter, so we're in appropriate units. All we have to do is plug everything in. So we take 0.785 grams per liter, multiply it by our liters, so 3.1 liters. Okay, when we do that, we get that the mass of this substance is 2.4 grams. And that would be our answer. Here's the kicker. This next one's going to be the hardest one you kind of see with these types of problems. If gold cost $475 per troy ounce, and the density of gold is 19.3 grams per cubic centimeter, how much would a cube of gold, whose length is 5.85 centimeters long, be worth in dollars and cents? Hint, there's 12 troy ounces in 1 pound and 454 grams in 1 pound. Those are probably your conversion factors. Well, when I look at this problem, I need to figure out price. But in order to figure out price, I need to be able to figure out the mass. So I'm going to write down I need mass so that I can get dollars. I know this is a solid, so that's grams per centimeter cubed, and I know my density equals 19.3 grams per cubic centimeter. In order to find my mass, I need my volume before I do anything else. So let's go ahead and start working for our volume. I'm going to go ahead and square this bad boy off. So we're about to write really small here, so bear with me. Volume is going to be, it's a cube, so our volume for a cube is length times width times height, or other words, length cubed. So 5.85 centimeters, and we're going to cube that. Okay, what that gives me is whenever I multiply that out, I get 200.2 centimeters cubed. Okay, so now we have our volume, we have our density, now we can solve for our mass. Mass equals density times volume. Other words, if we plug in what we have, 19.3 times 200.2, and that's going to give me a mass of 3,863.9 grams. Okay, we're going to mark that real quick. Now, what we're going to have to do is convert that grams into our into our money. To do that, it's going to take several units. This is why dimensional analysis is important, so that you can cancel units out. So I'm going to take my known over 1. So 3,863.9 grams over 1. And we want to cancel out grams first. So that means grams needs to be on bottom. And what our conversion units have is we have grams to pounds and pounds to troy ounces. So this only gives us one place to move. So we're going to have to do pounds. We know 1 pound is 454 grams. Next, we want to get rid of pounds. So we want to get to troy ounces. So 1 pound is 12 troy ounces. We'll put TO for troy ounces. And finally, we want to get to money, and we got the cost. If you look at the very beginning of the equation, 1 troy ounce cost $475. Okay, we've got rid of troy ounces because we have it on top and bottom. We got rid of pounds because it's on the top and bottom. We got rid of grams because it's on the top and bottom. We're left just with money. The question asks, how much money is it going to cost? So now we multiply and divide, and we get that this cube of gold is worth a whopping $48,511.41. That is the hardest type of problem you will get with density. Let's continue with the lecture. Let's talk about specific gravity. Specific gravity is the ratio of density of a substance to the density of water, which is, in our case, 1.0 grams per milliliter. So you can compare the density of a substance to 1. We will never compare our specific gravity to anything but water in this class. So you can kind of think of specific gravity as unitless density in this case. Specific gravity tells us whether something will float or not. If the specific gravity of two substances are given, the higher density or higher specific gravity is going to sink in the lower specific gravity. In other words, your lower specific gravity or lower density is going to float. We've covered this with our buoyancy. Okay, this is just another way of saying it. So let's work some more practice problems with these. If you're constructing a raft which weighs 2,172 pounds and has the dimensions of 120 inches by 60 inches by 10 inches, would this raft float in water? Hint, 1 pound is 454 grams and 1 cubic inch equals 16.39 cubic centimeters. Okay, again, this is going to be kind of similar to your last problem. It's a very hard and in-depth problem, but you can get through this one, you can get through any specific gravity problem. What we need to understand is we want something to float. So if it's going to float, we need to see that it needs a specific gravity. So I'm going to say SG needs to be less than 1.0, or the specific gravity of water. Okay? What we're going to have to do here is calculate the density of this substance and figure out if it's greater or less than 1.0. Here's the kicker. We have our mass in pounds, but for a solid, we need to have it in grams. And then with our volume, we have to calculate that. And then we have to take that and convert it into cubic centimeters. So we got a lot of different calculations here. It's not terrible. Again, we're just trying to figure out density equals mass over volume. We're just having to figure out our mass and volume. So I'm going to square this off, and let's go from here. So let's do our mass first. We can either do volume or mass, it doesn't matter, but I'm going to do my mass first. So I have 2,172 pounds, and I'm going to put that over 1. I want to convert that to grams. So like we did last time, we got to get rid of pounds, so we have pounds on top. So that means pounds needs to be on bottom this time, and we want to get 2 grams. Well, our relationship gives us that there is 1 pound in every 454 grams. So if we multiply that out, I get a ridiculous number of 986,088 grams. So 986,088 grams. So this can be our mass if you just want to know that. Let's do our volume. Okay, so our volume for a raft is length times width times height. We're going to assume this is a rectangular prism raft. Okay, so we're going to say 120 inches times 60 inches times 10 inches. When we do that, we get 72,000 cubic inches. Okay, notice this is not cubic centimeters, so we are going to have to convert. So what we have to do is take our 72,000 cubic inches, put it over 1. We have to get rid of inches. We are given a relationship that 1 cubic inch is 16.93 cubic centimeters. So I say 1 inch cubed is 16.39 centimeters cubed. When I multiply that out, we get that there is 1,180,080 cubic centimeters. Okay, so those are our two numbers. That's our volume. I'm going to put a V right there. Okay, now it looks like we've ran out of space on our deal. So I'm going to give you a second, write down what you need, and I'm going to erase this side over here, the left side. Now, in order to find our density, because we're trying to figure out is this going to float or not, we need to figure out is the density greater than water, which is 1.0. Okay, we take density equals mass over volume. So our mass in this case is 986,088 grams, and our volume is 1,180,080 cubic centimeters. Once I divide that out, I get a density of 0.84 grams per cubic centimeter. And if we compare that density of water, which is 1.0, that means it is less than water. So the answer is, will it float? Yes. Isn't it great when we work out all this math just for a yes or no question? Beautiful. Okay. And so let's finish up our lecture now. Can density change? Well, think about this. If you heat up a substance on a molecular level, those molecules are going to move more. If it's a liquid, it has a lot of molecular freedom, or a gas has a lot more molecular freedom than, let's say, a solid. So if we heat up a gas, those molecules can move more. That means that volume can change, thus changing the density. But for a solid, you heat a substance up, those molecules are going to stay and vibrate in place. They might vibrate more vigorously, but it's not going to change the volume. So can density change? To a degree, yes, but it depends on the state of matter that you are in and what this substance is. So think of whipped cream, okay? With your whipped cream, it's originally, when you make whipped cream, you have heavy whipping cream in a liquid form. You put that in a bowl, then you start mixing it. It suddenly turns into a solid, traps a lot of air in there, and it doubles, triples, quadruples, depending on how good your whipping cream is in the amount of volume it takes. And if you take a little bit of that whipping cream, it's going to feel a lot less dense than the entirety of that liquid that you poured in there. So can density change? Well, yeah, but it just depends on the state of matter and the fact that what that volume is in that state of matter. Okay, so congratulations, you made it through the density lecture. Probably was a little bit longer than you wanted it to be, but we made it. we were able to connect bone density to jewelry to the ability to float, let's say even a car battery, and the beautiful marketing of Dawn dish soap. We learned that the density of a substance can be calculated, and it is dependent on the mass within a certain amount of volume of a substance. For my teachers in the group, okay, you can check down, you've seen in all the slides, there's the next gen science standards and other state science standards I'll have that goes with this lecture in the comments, or let me correct that, it's going to be in the description. Also, if you're a student and you want some extra practice, I got some of the problems we worked out in class along with other problems as a downloadable link in the description. If you got questions, always hit me up in the comments, or if you're one of my students, hit me up in class. It'll be all good. In saying that, keep up the good work in the classroom, and I'll see you next time. Best of luck in what you do. See ya.